All right, welcome back. We're going to finish up section 4.2 in this video. First, let's look at example 6. We're going to show that a square matrix A is not invertible if and only if 0 is an eigenvalue of A. And before we prove it, the proof is actually going to be really easy, but I think it would help to look at a little example of it. This is back in 4.1. We have this example 6 here. One of the questions was, are these matrices from these examples invertible? And we showed that the A matrix from example 6 was not invertible because the second column is -2 times the first column. So the columns are linearly dependent. We have a solution of AX equals 0. Like if you do -2 times the first column plus -1 times the second column, you'll get 0. And yeah, we also saw that here, that multiplying A times this vector here gives you 0. And in other words, if AX equals 0 and X is not a 0 vector, it means that that X is an eigenvector corresponding with eigenvalue 0, because this is the same thing as 0 times X. So yeah, let's write out that reasoning, but looking at the invertible matrix theorem first, we see that everything up through part 9 was the original invertible matrix theorem, and A is invertible is equivalent to the null space of A being just the 0 vector. And another way of saying that is that the only solution of AX equals 0 is the trivial solution x equals 0. Because the null space is the solution set of this, the set of x's that make this work. And if it's only 0, that means the columns of A are linearly independent, and it means A is invertible. Okay, but if these are equivalent, it means if one of them is true, the other one is true, and it means if one of them is false, the other one is false. So if A is not invertible, that is equivalent to the null space of A is not just the set containing the 0 vector. And another way to say the null space of A is not just the 0 vector is that there's something that's not just 0. There's a non-trivial solution of AX equals 0. And again, that non-trivial solution we're talking about is an x vector that's not equal to 0. But that's true if and only if AX equals 0x has a non-trivial solution. Because, of course, the 0 vector and 0x are the same thing. So this is just the definition of 0 being an eigenvalue, because there is a non-zero vector x such that A times x equals the eigenvalue 0 times x. Okay, so yeah, that is the proof of that. And an equivalent way of saying that A is not invertible if and only if 0 is an eigenvalue is that A is invertible if and only if 0 is not an eigenvalue of A. And that is how we can connect part 11 to this. And by the way, part 10 came from the chapter about determinants. It was theorem 3.5, but we'll just throw it in here. So we're adding more and more ways we can describe invertible matrices. So yeah. All right, let's look at example 7. Example 7 says, suppose A is both diagonalizable and invertible. Well, it's diagonalizable. That means A can be written as P dP inverse with D diagonal. And by the diagonalization theorem, we know that the diagonal entries in D are eigenvalues of A. And we also know that since A is invertible, we know those eigenvalues of A are not 0. And if none of them are 0, that means all of them have reciprocals. Like you could do 1 divided by any of these eigenvalues, and you're not dividing by 0. So that's a big hint for what D inverse is. So, first of all, we can tell that D is invertible because it's already in echelon form because none of these diagonal entries are 0. So it's in echelon form and all of diagonal entries are pivot positions. So D is invertible. It has C pivot positions. And let's see what the inverse would be. Well, if we take D and we multiply it by this matrix that has the reciprocals of all of these eigenvalues of A in its diagonal entries, like so, then we can see that this is going to come out to be the identity. Because, like, let's say we're using the row column rule to calculate a few entries of this. So like if we do row 1 of D times this thing I'm claiming is D inverse, you're going to do lambda 1 times its reciprocal is going to be the number 1 plus a bunch of zeros when you keep going with the row column rule. If we get to row 2 column 1, we're doing 0 times this non-zero thing plus this non-zero thing times this 0 plus a bunch of other zeros. So this is going to be 0. And you can see why everything else is going to be 0, maybe. And if we keep doing this in other rows and other columns, you're doing the row column rule to get like one of the diagonal entries, the result will be 1. And everywhere else, the zeros will line up with non-zero things, and you'll get 0. So yeah, multiplying D times this matrix gives you the identity. And I also claim you could do it the other way around. You could check it if you want, that if this is D inverse here, we have that D times D inverse is the identity. And if you want, you can check D inverse times D is also the identity. Okay, now that we have that, we now know that all the different factors that make up A are invertible. So that means when we find A inverse, we know we can multiply the inverses of these different parts in backwards order, and that will multiply to make A inverse. That was a theorem that you get these inverses of the factors in backwards order from chapter 2. And also, let's notice that P inverse inverse is just P. So we have P times D inverse times P inverse. And what does that tell you? Well, the diagonalization theorem now applies to A inverse as well. Because A inverse is now written as this invertible P times diagonal matrix times P inverse, and the entries in the diagonal of D inverse are the eigenvalues of A inverse. And also, the columns of P are eigenvectors of A inverse. And the columns of P, by the way, are also the eigenvectors of A, because both A and A inverse can be written as P times a diagonal matrix times P inverse. So yeah, using the diagonalization theorem and this thing we proved in example 6, we can see that the eigenvectors of A inverse are the same vectors as for A, and also the eigenvalues of A inverse are just the reciprocals, like the regular multiplicative number inverses of the eigenvalues of A. Cool beans. And yeah, I just wanted to mention something. Something strange has been occurring to me because right now it is the Friday after week 1 of the spring semester 2026. And in class, y'all were just learning how to do Gaussian elimination in section 1.1. And it's just occurring to me how much linear algebra there is between where you are in that timeline versus where we are when you're watching this video in chapter 4. Linear algebra is just such a big, complicated subject, and how much more complicated the stuff we're doing now is than then. But something I love about teaching linear algebra is just that every semester I'm always impressed by how much students can learn and how well they can figure out this complicated stuff. So I'm crossing my fingers, hoping you've caught up with the class thus far by the time you watch this video. If you have, good job. Give yourself a pat on the back because I just saw you in class a couple days ago, and I can tell you if chapter 4 is making any sense at all to you, then you have come a long way and you've learned a ton of math. So, congratulations. And the homework's gotten a lot harder too. You gotta think pretty abstractly here. So I will let you get to this homework in a couple months when you watch this video. Good luck with it. Remember, it's always a good idea to work in a place you can get help, such as office hours or with friends, etc. All right, I will see you later. Bye.